All right, so we already mentioned that if you've got a neutron to proton ratio that's too high, you are going to have some kind of issue and you're going to have to do some kind of changing the nucleus. It's not like we're doing it. The nucleus just decides it. The nucleus is like, this isn't working for us. And this is the crazy part. I just think this is so fascinating because it seems like magic to me. You can start with calcium and calcium 2040. And if the numbers of, if that neutron to proton ratio, if it weren't right, and there was just too much instability trying to hold this thing together, and the nucleus was just giving up, basically, what it'll do is it will actually take one of these blue neutrons, turn it into a proton, kid you not, throw out some energy, and also throw out a particle that remains, a leftover particle. When you turn a neutron into a proton, you can end up shooting out an electron. Crazy stuff, but this is what we're talking about for radiochemistry. When you turn a neutron into a proton, you change the element. So if you think back in history, they've always tried to turn, something into gold. So technically you can turn lead into gold if you wait a very long time and you have a very long process and you have it go through several radioactive conversions, but it makes such a small amount that it's just not even worth it to do it. So you don't have to know what the conversion is. And you all should be aware that you can have a proton to neutron ratio that's too high. And so what happens in that case is that a proton can be turned into a neutron. So by grabbing an electron from another place. So that can happen. And then, but what you need to know is that there are different patterns specifically that decay follows. Like basically for this to happen, if you turn something into something else, it's going to emit certain things every time. So these are the certain things. I've got a nice little list here. So I'm going to bracket these together. So these are the things that generally come out, like in this one, that come out naturally. So if something is radioactive and the atom is fixing itself, then you are going to have alpha decay, beta decay, positron decay, one of those. And then you will also release energy. Sometimes it's a gamma ray is how it's released. Sometimes it's just some regular energy. It's not as high energy as a gamma ray. So how do these work? All right, so I'll show you some reactions coming up. But the first particle is an alpha particle. This is the largest of all of the particles. You can kind of see it in the picture. This is the largest of all the particles. And when they first were discovering these particles, like they used the words alpha and beta because they didn't know, and gamma, because they didn't know what they were. And so you still might see an alpha written in a reaction, and it's totally fine. These two are interchangeable with each other. These two are interchangeable. So the alpha particle is the largest one, and so it's really heavy comparatively, and so it can't move very far. And so it turns out that it does release this, an atom will release a helium nuclei called alpha, also, consisting of 2 protons and 2 neutrons. Notice there's no electrons in there, so it is positively charged. This might seem concerning, but paper will stop it. It does not move very fast because it's so large, and it can't move through very many things, again, because it's so large. So paper will protect anyone from it. For sure, skin. Skin is much thicker than paper. If we move on and we look at a beta particle, know that both of these, see how there's a beta in both those cases? So they both are actually called beta decays. And this is a positron type of beta decay, and this can sometimes be called a negatron. Sometimes people just call it beta decay, and they just expect you to know that most beta decays are negative. But you can have positron decay. This tends to happen with the smallest elements, and then this happens with the bigger ones. So both of these are high energy electrons that are released, and this does have a negative charge. Know that skin will stop it though. So if skin will stop it, if you had your hand right up next to it, you could end up with like a little bit of skin damage if you were like right there. It's not saying that it doesn't cause any damage, but it's not going to get into your organs or cause any damage in your organs. And then that's the same for positron decay also. If you move on down to gamma decay, lead is what takes it to stop it. This will move right on through your whole body, and it can cause damage like to internal organs and stuff. This is more than an X-ray moving through your body. We will also look at neutron and proton, and these elements can be given off, and they can also use, this one can be used medically to find tumors. You can use radioactive elements as a whole also to treat tumors, because an alpha particle, it moves such a small distance. And same for these. If you can actually insert it into a very large tumor, it can't go past like the boundaries of the tumor. And so it's a great way to get a tumor smaller. So I always like to put the context of nuclear chemistry in that context of, we also, even though things can be not good for us, we also use it in a lot of really, really good ways. So keep that in mind with radioactivity. We can turn around and use these for really, really cool things. We'll look at protons and neutrons later on. Neutrons can be given off in a reaction, but they also, and protons, those both can be used in bombardment reactions, which is where you kind of like throw it as something like a baseball. So can alpha particles. Those can be thrown at things like baseballs. And those are all the particles we're going to be looking at. One last little tiny note, as I zoom into this, I do want to point out that you need to use these numbers when you're writing these, because it helps us do the math. You'll see the math is really, really easy. And I want to point out for everything except for these two guys, because they're kind of weird on how we write them. Right here, this is our number, just like before, that same notation where the top is the protons plus the neutrons. This is just the protons. I'm going to scooch down here. Again, this is protons. This has no neutrons, so it is the protons plus neutrons, but neutrons is 0 in that case. Over here, this has 0 protons because it is a neutron, right? So it has 0 protons. But if you look at the top part, it's acting weird. But if you look at that top number, again, still protons plus neutrons. So even though my protons are 0, I've got 1 neutron because it is a neutron. So there's that. And then the gamma is not written with any, if you wanted to, you would write it with like 0, 0. Now let's look at these two guys on the top. Again, they do not have any protons. This represents the total mass. They don't have any neutrons. So yes, there technically is a tiny, tiny mass to these guys. But for the sakes of our reactions, we just call the mass of those ones as 0, because they're a factor of 1,000 off from everything else that we're looking at, from every particle that we're looking at. So this is still, that's the mass number. So basically it's 0. Now this is how we write these bottom ones. Yes, this is supposed to represent the number of protons, but this is obviously an electron. So in this case, we actually are writing the charge right in that position. You'll see why we do it that way. Coming up, this kind of does act like a proton, kind of, I guess, in terms of the charge, but it doesn't act like it in terms of what it can do. This one right here, I don't know, it's like negative, it's a negative proton. I don't know. There's no real good way to explain it except for me to tell you that in just a second, when you see us do our reactions, you'll see why writing it like this helps us get to the right answers for all of our equations.